So right now you're looking at the inside of the eye of a 4D creature, and I promise that by the time I'm done explaining it, it will make a little bit more sense. Since I was a kid, I'd heard of a fourth dimension as a meme or a mathematical abstraction, or just an alternate reality. To be clear, I'm not talking about time here, but about adding just a regular spatial dimension. Picture a 2D world and what it would be like to add depth to it. To its inhabitants, this new dimension would be very confusing, but to you and I, it's clear that it's just nothing special. If you rotate things, the dimensions are totally interchangeable. Our natural question is if we can visualize this extra dimension in our world, but unfortunately, it's perpendicular to all of ours, so not really. But a couple of works have done a really good job of using analogy or projecting 4D worlds to a 2D screen to give us an idea of what it could be like. However, our brains are able to understand the 3D world through a 2D retina. But understanding a 4D world with a 2D projection is more like trying to understand a 3D world from a 1D line. It's two-dimensional jump. So what if instead we could expand and try to visualize a 4D world through a 3D sensor? That's what this project is trying to do. Now before we get to rendering 4D worlds, let's remind ourselves of how 3D worlds are rendered, as is typically done in video games. The objects you see on screen, though they look very convincing, are actually just points and lines, with most of the texture coming from triangles, the primitives that are most used to constitute surfaces in 3D. Now, while points and lines project very easily from world to sensor, primitives like triangles or spheres require more complex warping or rasterization. So in this first simple experiment, we'll build our objects out of just point and lines, also called vertices and edges. Now the first object we'll build is a hypercube, or 4D cube. And to figure out what its vertices and edges should be, we can just extrapolate. As we go from a 1D line to a 2D square to a 3D cube, each time we just copy over the previous object, translate it in the new dimension, and just connect every vertex from the old to the new. So we can do the same here and copy our cube over into the fourth dimension and connect the vertices. This gives us 16 vertices and 32 edges in our hypercube. And you can ignore most of the rest of the code, except for the pose, it's not really relevant right now. So now we have a 4D object, but how do we visualize it? An eye and a camera are fundamentally the same thing. They're both projecting the 3D world onto a 2D screen or retina. But what would a four-dimensional creature's eye look like? Here again, we can extrapolate. It turns out that in all dimensions, the aperture is just a point. The sensor itself ends up being one dimension less than whatever the world is. This has to do with the focal length and how a light hits the sensor, but we won't get into it here. Anyways, now we know that our creature's eye needs a 3D sensor. So we need to figure out how to render to it. And here it's good to look again at the equations of a camera in 3D. For example, on Wikipedia, you can find this very useful equation, also called the perspective projection model. It looks complicated, but in a nutshell, it describes how you can take a point, transform it into the sensor frame, and then just scale it until it's at the sensor focal length, and you get the pixel coordinates. Put all this together, and we have our first renderer prototype. First, we transform the points into camera frame, and then render them with Three.js. This is what the code looks like, or at least it's the pseudocode, because the real code has a little bit more complexity to it. Nothing important though. The first part is just about projecting, and the second part is how we create those primitives like spheres and lines to show them in the 3D sensor. And here's what it looks like. I've added camera controls so that you can kind of move around like a creature would and experience the world through this sensor. And on the right and left, I've added some extra projections just to help me understand a little bit better where everything is. And it's cool to see how when you move around in 4D, the object's projection in the sensor moves as well. For example, when you get closer to it, the object gets bigger. And this makes sense because it's the same with a regular camera. As you get closer to an object, it gets bigger in the picture. So this is very cool, but I still want to go further. I want this to feel grounded, like a real world, like a 4D planet that could potentially exist. And so I think the first thing we need is a floor. And to understand what a floor looks like in 4D, we need to think a bit about gravity. Just like in our world, because of gravity, planets would still be very spherical. And if you zoom in on the surface, it would look quite flat with a constant gravity vector. So that's a relief. We can keep using z as the main gravity direction, which means the other direction are perpendicular to it. And so our flat floor can be represented as a grid of 3D cubes, which can be a bit confusing because it is a surface, but, and this is worth remembering, in 4D worlds, 3D objects are surfaces. And here is code to create a grid of cube that we can then use as our floor. It's got 3 nested loops, one for each dimension, and we create the vertices and then connect them with edges. Now I should probably mention camera controls. So in 3D, there's 3 rotation directions to rotate a camera in, and we typically name them by the vectors perpendicular to the rotation plane, x, y, and z. But in 4D, there's actually 6 fundamental rotations. They correspond to the rows and columns of the rotation matrix that are non-zero. And so in 4D, there's no such thing as a rotation axis because there's no unique vector that's perpendicular to a plane. In video games, cameras are typically on a swivel on a vertical axis, meaning there is no tilt and only pan in the off. So here we can use gravity to our advantage and notice that XY, XW, and YW rotations keep our character upright, while XZ looks up and down, and the remaining 2 we just forbid, the same way that tilt is forbidden in 3D games. Translation is just X, Y, and W, with X being forward backwards, the other 2 being sideways, and Z being jump. Having 4 rotation and 3 translations makes controls a bit complex, but that's okay, we can assign them to keyboard keys. And for fun, why not add some physics? So we add vertex forces, for example if they're penetrating the ground, or gravity, and accumulate them at the center of mass. Then we can do some simple Euler forward method, and okay, that's not exactly right. Much better. Okay, so we have a cube and a floor and physics, and you'll notice that I added a hyperpyramid in there, just for fun. I've also made it so that you can push objects around, and by getting them to the center, you collect points. And the hope was that by making this more like a video game, I would eventually train my brain to understand the 4th dimension a little bit better. I'm not sure if that worked, but you're free to try. Link is in the description. Anyways, this is fun, but I think you'll agree that it's missing something. I think it's time to add a dash of color. Which means it's time to remind ourselves how triangles are traditionally rendered, by having their points projected in the center frame, and then doing intersection tests for each pixels. Now in 4D, we need to replace triangles with tetras, but the process is the same. And here it is working in our little experiment on CPU. So for each voxel, we figure out whether that voxel is inside the projected tetra, and fill the sensor accordingly. Now for more complex scenes, we just need to break down everything into tetras. For example, a cube can be broken down into 5 tetras, and the floor is just a bunch of cubes. So let's try rendering a cube and floor, and increase the voxel resolution of our sensor. And because my computer is starting to make jet engine noises, I think we're starting to reach the limit of the CPU. Which means it's the perfect time to take the GPUs out of the oven. And because I don't want this video to be 10 hours long, I'm going to keep the description of the GPU pipeline to a pretty high level. So in the first stage, we parallelize transforming of the vertices to all the GPU threads. And this is pretty simple. Next, we need to set up an acceleration structure. This is because if we have n tetras and m voxels, that gives us n times m intersection tests, which is way too many. So in this stage, we assign each tetra to a thread to figure out which cells their bounding boxes overlap with. And in the next stage, we assign each voxel to a thread and do the intersection tests only with the relevant tetras. Now by stage 4, all the voxels in the sensor are filled. We just need to render them to a 2D screen. For this, we use DDA ray traversal. This can be done as a simple fragment shader that renders directly to the screen. It's also worth considering the data transfers. For example, all the heavy stuff like vertices, tetras, and textures only get transferred to GPU at initialization. So after physics and camera movements at each frame, all we need to transfer are the object and camera poses, and then the 4 GPU stages from before can just compute directly to buffers on GPU memory. The implementation is just a single file, about 3,000 lines, using WebGPU because it lets me do compute shaders for the first 3 stages and a fragment shader for the last. Here's the moment of truth, and it works. And I'm very happy with how quickly it renders about 1 million tetras with a 96 x 96 x 96 voxel resolution on my laptop. The one thing that's missing though is textures, which if you don't know, is typically done with UV maps, which are basically a 2D grid, and each vertex is assigned a coordinate on this grid from 0 to 1, and any point in the triangle can be colored using interpolation. So for 4D, the grid just becomes 3D and the triangles are tetras. And here's the result. Textures are working. We can now texture any object how we want, and the textures don't take too much space because I've kept them quite simple and low resolution. This is pretty exciting because it finally feels like we're dealing with real objects, and the performance is just fine. One issue I did notice is when I added more resolution to the floor, things got pretty slow. And this makes sense because in 3D, the number of tiles grows with the square of the floor resolution. But in 4D, the number of cells grows with the cube of the floor resolution, and each one of these cells has 5 tetras instead of 2 triangles. So instead, we can define a custom floor shader that we include in stage 3. And I was thinking something like an island because it naturally restricts the player movement and is quite simple. And for the island shape, I use a sphere, which, again, remember, 3D objects are surfaces in 4D. And here's how it looks. I added some waves as a function of time in the shader to make it feel more dynamic, and I'm pretty happy with the result. Now we need some trees, so let's imagine from first principles what they could look like. The trunk is still probably a gravity-aligned vector to support the weight, while the foliage remains a sort of sphere to absorb the sunlight. And one useful method to model 4D objects is to cut them into 3D slices. So here we do slicing in the Z direction. And in our world, the slices would be circles, but in 4D, they're spheres. So we may need to take a step back and think of how we could model a hypersphere in the first place. So to make a sphere surface in 3D, you can take a grid mesh and roll it like a cylinder, then adjust the red eye. So in 4D, we can go one step further and reuse our floor grid, then roll it into spheres the same way and change the red eye. And this is what the code looks like. It's exactly the same code as the floor grid, just with spherical vertex coordinates. And there we go, a hypersphere. I don't know what I expected, to be honest, but I think it's correct. So to get back to our tree, we can just take this hypersphere and add more Z spheres, while giving each of them an appropriate radius depending on whether they're in the trunk or in the leaves, and update the textures. And here's the result, a 4D tree. It looks almost disappointingly normal, but I guess that's because hyperspheres are just so regular. Anyways, now I'd like to go beyond plants and make a small animal. How about a hypercrab? So for the body, I just redo a hypersphere, although it's a bit more squished in the Z direction. And then for each legs, I just make one tetra widening and then a tetra thinning at the end. I also animate the vertices so that it looks like it's walking around. And although it looks normal at first, when you start rotating around it, things definitely get a bit weirder. On the island, I also make it walk around and go down in the water when it reaches the edge and then reappear somewhere else. I also realized that I can reuse the hypercrab leg concept to make a palm tree, which looks way cooler than a regular tree. And you'll also notice that when we start rotating around it, things definitely get a little bit weirder. I'm still trying to wrap my mind around the concept of 4D rotations, and both the crab and the palm tree are still really hard for me to understand when I move around them, but I think they look pretty cool, so I'm happy. And finally, I want to add a little escape pod on the island, which implies that you're an astronaut that crash landed on a 4D planet. Except I want to add a twist. So imagine in 2D if you had a shell with a star inside. No matter how you went around it, you couldn't see the star. But once you add the third dimension, by going sideways, suddenly you can see the insides. So the same is true in 4D. So if our pod was a 3D object unnaturally landed in a 4D world, you could also see the inside by moving sideways in 4D. And I do this by taking a hypersphere and cutting out only a strip in the W dimension, which again requires very little code change apart from the textures that I at first screwed up so that it looked like an egg, but then later fixed, and here's the result. Okay, so this is what it looks like when you rotate around it in the usual 3 dimensions. You can't see the inside. But as soon as I start rotating around it in the 4th dimension, weird things happen, and suddenly the insides are inside my camera sensor. So this is still a bit confusing to me, and I'm still not sure I fully comprehend it, but it does look pretty cool, and I think it could make for a cool puzzle. So I'm definitely keeping it for now. Here the sensor is cut out, just so you can see the inside. Now it's time to put all of these together. So here I start off by having the engine render only a thin slice of the sensor, essentially just making it a regular 3D camera. And you'll see that as I move into 3 dimensions, things look pretty normal. But when I move in the 4th dimension, that's when things get pretty confusing with objects appearing and disappearing from the scene. Now I want to add a story point in the game where your eye or camera gets upgraded to a full hypercamera. And ideally this should make it easier to solve certain puzzles or navigate around the island. Although I'm not sure I've figured that part out completely yet. And I also need to add colliders to make sure that you can't go through objects. Plus, there's a couple of bugs that need fixing, such as tetra clipping when they're at the edge of the sensor. But overall, I'm really happy with how this turned out. Now I have an engine that I can build 4D games in that's pretty novel. And who knows, maybe over time, by playing with the 4th dimension, our brains will end up having an intuitive understanding of it. We'll see. And that's all for now. Thank you for watching. I really hope you enjoyed Hypercamera. And if you want to try any of the demos, there's links in the description. And stay tuned for the next chapter. Okay, bye for now.